Hi all, I'm Meghamala, working as Assistant Professor from Institute of Aeronautical Engineering. And today I'm going to talk about Analysis of Synchronous Sequential Machines Part 2. So in the yesterday's class, we have discussed what are the synchronous sequential circuits. Basically, we discussed about the sequential machines. So under the sequential machines, we discussed that the output always depends on the present input and as well the past inputs. The history of the past inputs and as well as the present state of the inputs, the output is always depends upon, and this is what about the sequential machines. And as well, we have discussed regarding the synchronous sequential and asynchronous sequential. So synchronous sequential machines are nothing but they are the machines where it works or else it takes the helps of the clock signal. So in the clock signal, with the help of the positive edge and the level edge sensitivity of the machine, we can able to determine the outputs properly. So in the edge triggering and as well as in the level triggering, we discussed about the level triggering. The level triggering are nothing but these are the elements, these are the storage elements where they store the 1 bit of information, and here in the level sensitivity of the machines, we discussed about the most probably will be using the latches. In the level sensitivity, we use the latches, whereas in the edge sensitivity, we use the flip-flops. So here in the level sensitivity, we discussed that the output, the abrupt, if you observe the abrupt changes in the output, it means that if you have changed any input abruptly, suddenly if you want to change any input suddenly in the input side, then automatically the output will be changed. So abruptly, if you are seeing any output changes, it means that there is a change occurring in the input abruptly. That is, suddenly if you are changing anything in the input, the same will reflect in the output. So coming to the synchronous sequential circuits, basically the synchronous sequential circuits, if you observe the analysis, that means how the performance or else the output, how they are the performance of the output is calculated based on the clock signal that you are assuming. So in the clock signal as well, there are many constraints to be calculated. So one after the other, we will discuss cleanly. Coming to the synchronous sequential circuit. So the output of sequential circuits depends not only on the present value of the input, but as well but also the state of the circuit. So it doesn't mean that, it means that the output doesn't depend only on the present state of the input, but as well this state of the output. So coming to the state is nothing but in the sequential machines. Especially when you are explaining something about in terms of the sequential machines, always remember that we must consider a particular state. Okay, so there is a transition between the states. That means the information or else the data can be carried out between the state. The data transmission can be carried out between the states. Okay, so and also there are many constraints with respect to the state register we have discussed yesterday. So state register is nothing but the register which holds the information, the data which is present in the register. That particular data is nothing but the data of the next state and as well as the present state data. The data which is accumulated in the particular register, that register consists of the next state information and as well as the present state information. So we are calling such information or else the register is nothing but the state register. So here the sequential circuits, they are nothing but the output is drawn with respect to the present state and as well as the present state inputs. Okay, and the state of the circuit is determined by the previous values of the input. So basically, what is a state? As I said, we have different types of states, S1, S2 and so on. So basically, what does the state holds? The state holds the previous values of the input. The information which is present in the state is nothing but the previous values of the input. So the values, the machine which is having the previous inputs. For example, I have the inputs I1, I2 and I3. So for state S2, the information should have the state S2 of the previous information, that is I1 or like that, I1 or I2. So here the state of a circuit is determined. How the state of the circuit is determined with respect to the previous values of the input. Only with the previous values of the input, the particular state of the machine is determined. And the sequential machines, they have memory, and output depends on the sequence of the past input. So here when it comes to the memory, so in the storage elements, usually we will store the memory, right? So the storage elements are nothing but the latches and flip-flops. They both goes with the level edge triggering, level edge sensitivity, and as well as the edge sensitivity, right? So here the sequential machines which have the information or else a memory and its output, the output of that particular machine or the memory depends on the sequence of the past inputs. So here, as the sequential machines, they are nothing but they holds the informations of the history of the inputs, right? History is nothing but the past inputs. So here also the sequential machines which holds the memory, where it the output of a particular sequential machines, it depends upon the past inputs, the sequence of past inputs. And these circuits use memory elements. So as the sequential machines, they store the information, they store some storage elements, so storage devices, right? So here they have the memory elements. That means they store the memory, right? So the memory elements are nothing but the flip-flops, and to store the current state of the system. So maximum we'll be using the flip-flops, okay, compared to the latches. So as well, there's nothing much difference between the latches and flip-flops. They both are the same storage elements. They store the one bit of information, and these are the transparent devices. Based on the clock signal, we will be able to decide, or else we will be able to confine which is a latch and which is a flip-flop. Which one is the level triggering and the edge triggering. Okay, so here these circuits use the memory elements, nothing but the flip-flops. So under the flip-flop, we have discussed different kinds of flip-flops, isn't it? The D flip-flop, toggle flip-flop, JK flip-flop, master slave flip-flop, set reset flip-flop, and so on. So these are the memory elements where they store the information, and these memory elements, with the help of these memory elements, the synchronous of the sequential machines can be carried out. And in a synchronous state, all the storage elements are triggered by the same clock signal. So here in the sequential machines, for each and every machine, the similar clock, the same clocks will be help us to trigger the same clock signal. So here the storage elements are all the storage elements, all the flip-flops, all the devices, all the flip-flops, they contains the same clock signal. The same clock signal can be carried out for each and every storage device, that is flip-flop 1, flip-flop 2 and flip-flop 3. So how many storage elements that you are considering? So for each and every storage element, the same clock signal is been given. So here all the storage elements, the same trigger, the same clock signal are triggered with respect to each and every storage element. So you don't see any different clock signals are not given to each and every flip-flops, whereas for different flip-flops, for different storage element, the same clock is being triggered. Then, since all the storage elements are elements of a synchronous elements are connected to the same clock, we can model the system. So we are saying that the same clock is been triggered to all the memory elements. So this is how with the diagram in the figure, we can see how this same clock is been triggered to all the storage elements. So here if you observe, we know this is a storage element, right? So this is a storage element, and we see here the next state logic, and as well we see here the output logic. So output logics are nothing but we finally whatever the outputs that we are getting, the output logic will enable us to get that particular output. And here we have the clock signal. See, the same clock signal is being given for all the individual storage elements, for suppose D flip-flop. So here this is a storage devices. Okay, so the storage device that I am considering is a D flip-flop. So D flip-flop. So for this D flip-flop, my input is a D and Q is the output, and output they directly output I'm giving directly to the output logic. So output I'm giving directly to the output logic. And here the next state. What is this next state? In the yesterday's class we have discussed for each and every transition we'll be having the present state and as well as the next state. So next state will contain the output from which is obtained from the present state is nothing but the information is stored in the next state logic. So from there the elements from there, the actual information can be stored in the storage register or else the state register. So the state register consists of the next state elements and next state information, the logic and as well as the present state logic. So here in this particular diagram, I am saying that the very one particular single clock can be given for each and every storage elements. So here my storage element is D flip-flop. So here I am giving as a clock. Okay, and the clock, this is a clock, this is the output state register is being given to the output logic, and from the output logic the output can be obtained. So here if you observe, in the sequential machines we have a feedback, isn't it? So this is the next state, this is a present state, and this is output. So this is how the diagram says. This is the next state output, and this is the present state output, and this is the output. This is the feedback element. So the feedback. So whatever the output is obtained with respect to the present state, that is given as an input to the next state. So here the next state is holding the data which is obtained from the present state values, isn't it? So that's how we can say that the sequential machines are nothing but they hold the information where the output holds the information of the present state and as well as the past outputs, present inputs and as well as the past input, the history inputs. So the history input is nothing but the next state which is obtained from the present state value. So this is about the diagrammatical explanation of all the four statements. So we have next state logic given to the storage element flip-flop, and the output of that flip-flop is given as output of that particular storage element is being stored in the output logic, and from there we can observe the output. So each and every and here we have a feedback structure given to the next state logic. Okay, so if you observe here, the clock is a single clocks can be given. A single clock can be connected to the same clock. So each and every device, the storage elements, for different storage elements, the same clock can be connected. And in this model, the dashed box represents the storage elements, that is the D flip-flops. Okay, so each and every, for suppose, sometimes I can consider D flip-flops and sometimes I can consider RS flip-flop. So different types of flip-flops, different types of storage elements I can consider. So here in the particular example, this is the storage elements, that is a D flip-flop. And then the blocks outside the dashed box are combinational circuits. So here we call the this and this one and the next logic and the output logic. These are nothing but the combinational logic devices, combinational circuits. And then the next logic process, the next state logic, it processes the inputs and the current state of this system represented by the state register to determine the next state of the system. So how the next state of the system is being determined? The next state of the system is determined with respect to the process, the inputs and the current state of the system. So the present state of the outputs of present state, okay, the inputs and the outputs of the present state is nothing but these two will determine the next state logic. Okay, so unless and until if you are not getting any output of this present state, so where you won't get any next state logic. So if you are having a next state logic, it means that the information has been present. The information has been present in the information is given with respect to the present state output. That's how the next state will be. Logic is processed. So here the statements clearly talks about the next state logic process the inputs and the current state of the system. So which we are presenting it with the state register. So the state register consists of the information which is present in the next state and as well as the present state, and this present state is interlinked with the next state is interlinked with the present state. And to determine the next state of the system, so in order to determine the next state of the system, obviously we should have the output of present state is given as a feedback to the next state. That's how the next state is being determined. And then coming to the HDL description of a flip-flop. So here we will be concentrating more about the coding of how can a syntax can be written with respect to the flip-flop storage elements in the synchronous sequential machines. So here when you observe the HDL description, hardware description language, that means how can we write the program based on the description of a flip-flop. So here we see in general a D flip-flop is implemented using the basic logic gates. So using the logic gates we can implement the D flip-flop. So here at the clock edge, the D input of a DFF is sampled and passed down to the Q. So this is a positive edge D flip-flop, and here it is a negative edge D flip-flop. So we are just concentrating on the HDL description of a D flip-flop. So as for the D flip-flops, for the storage devices, we have a common clock is being used, right? So for the common clock, in the two categories, so for the positive edge and as well as a negative edge clock signal, so the representation of the positive and as well as a negative edge goes like this. So for this is a positive edge clock signal. So for this positive edge clock signal, you will observe D is the input and Q is the output, and for this we have a clock signal to be applied. So for this positive edge D flip-flop, we see a common clock is being given, a simple common clock. Okay, a simple common clock is given. And whereas if you observe the negative edge D flip-flop, for the negative edge D flip-flop, if you observe, we see a knob. It represents a negative edge. So here D is the input and Q is the output, where as it is representing the negative edge negative edge D flip-flop, such that here we see a knob. So it means it's a negative edge. So this is a similar difference between a positive edge and the negative edge for a particular D flip-flop, that is a storage element. And now we are describing the description of HDL based on the flip-flops. So for the positive edge D flip-flop, we see the sampling edge of the clock is rising edge. So here in the yesterday's class we discussed when regarding the storage elements, we have latches and flip-flops. For the flip-flops, we discussed about the positive edge and the negative edge, right? So rising edge and the falling edge. So this rising edge and the falling edge will be observing mostly in the positive edge and as well as the negative edge D flip-flop. So here for positive edge D flip-flop, so we see the positive edge D flip-flop is nothing but we have a plain clock signal given and Q is the output. So plain clock is given. So for this positive edge, the clock is the edge is a clock rising edge, while a negative edge is a falling edge. So here for this positive edge D flip-flop, we see the clock signal is to be a rising edge. So the clock signal is to be a rising edge, whereas for negative edge, so this is for negative edge. For negative edge D flip-flop, we see the negative edge we indicate with the knob, and D is the input and Q is the output. So here for this negative edge, we see the falling edge. Okay, falling edge of the clock signal. So these two are very similar to understand and as well as to remember. We have the representation or the description of the flip-flops are to be considered as negative edge and as well as the positive edge. So positive edge we are representing it with the rising edge of the clock signal, whereas negative edge D flip-flops is represents with the falling edge of the clock signal. And a full flip-flop usually have a reset, and that can be used to initialize a system to a known state. So here we have set and reset. So set and reset options we have. So if you enable the reset, that means what? If any error occurs, we can go back to the plain input normal given to the particular D flip-flop. So here particular flip-flop. So here the flip-flop usually have a reset button where it can be used to initialize the system to a known state. So in order to represent, or else in order to elevate some state, okay, from one state to another state, if you want to elevate some state, then you can go back to the reset button. So here, this is a Verilog code, which is for the positive edge D flip-flop. So this is a Verilog code. If you observe the Verilog code here, in 12 steps, in 12 steps, we have written the code. This is a positive edge D flip-flop. So for the positive edge D flip-flop, the clock signal will be a rising clock edge. So the clock rising edge will be observed in the positive edge D flip-flop. So in this code, if you observe, this is a 12 lines of code. First one is about the representation. Module is a keyword that we have to represent, and D flip-flop is a name of a module that you are considering. Okay, and the second one goes with the braces, and the third one is input, wire, clock, and reset. So here, wire is nothing but it is a vector. So here is in the net is a vector, right? So net is a variable. In the assignments, we have discussed about the nets and the variables. So under net, what sort of nets we have? So basically, net is nothing but a variable. Variable is nothing but a assignment operator. In the assignment operator, usually we are representing with the equals to, and to the left hand side, we'll see all the variables, and to the right hand side, we see the expressions. So assignment operator is indicated with the equals to, and to the variables we have the variables, it could be in terms of vector and as well as the scalar form. Okay, so vector is scalar, nothing but the difference if you observe in the vector and scalar is nothing but a 1 bit of storage devices. Usually, if you want to write or read from one circuit to the another circuit, if you want to write or read from one circuit to the another circuit, you will be observing, or else you will the reading and writing options can take place with respect to only 1 bit. So this is nothing but the scalar. 1 bit of transmission takes place between the clock 1 and clock 2 is nothing but the scalar. And when it comes to the vectors are nothing but it's a group of bits. So for example, now my circuit 1 is having a data of 2:0. So totally 3 bits of data I'm having. So these 3 bits of data at a time I can transmit from circuit 1 to circuit 2, or else I can transmit bitwise bit. So that is nothing but the vectors. Vectors you will observe the group of bits accumulated in one register, whereas the scalars are nothing but the 1 bit of transmission can take place between the circuits. So here, coming to the wire is nothing but it is a net. Nets are the variables. In the Verilog primitives, we have different types of variables. So one of the variables that we can consider is net. Under the net, wire is the keyword that we use. So here, input, wire, clock, and the reset. Clock and reset are the two elements that we observe in the flip-flops, isn't it? So clock is a basic element that we have to give, and reset is used to just to go back to the actual position or else actual thing. We will be considering this reset button, and this is a input D and Q is the output. So here the basic thing that you can consider when it comes to the variables is wire, clock, and reset. And then input. So input, what am I having is I'm having input D. So for input, wire D. So wire is a thing where it connects from one source to the another source, right? So here input wire D and the output register Q. So Q is the output. So the output is nothing but the information which is present, which is coming, which we are accumulating, that we stored in the register, right? So input, output, register Q, and then closing the braces with a semicolon. So semicolon is must, and then always at the rate. So always at the rate indicates that this example is under the behavioral modeling. So in the behavioral modeling and the data structure, data flow modeling, we discuss always at the rate. Okay, always at the rate and assign and always at the rate and assign. These two are the keywords. So for any algorithmic abstraction level or else for the data flow level, we'll be using this keyword. These two keywords are very prominent in order to write particular code. So it means that here this code is written in terms of always at the rate. So that means what? We are writing the particular code in the behavioral modeling. So this higher level of abstraction. So this particular module, this particular very low code we are writing in terms of behavioral modeling. That's why we are we are using a keyword called always at the rate. So always at the rate, positive edge clock and positive edge reset. So this example is about the positive edge D flip-flop. So when we are considering the positive edge D flip-flop, initializing of the positive edge or else the negative edge D flip-flop in the terminal list is very important. So always at the rate, positive edge clock and positive edge reset. Why? Because clock and reset are the two inputs that we are considering in our storage elements. We have clock and as well as the positive. Here we are present, right? In the third step, input via clock and reset. So we are considering the positive edge D flip-flop. So that's the reason positive edge clock and the positive edge reset. And here the condition goes like this. If reset Q less than or equals to 1 bit of data, that is 0, or else if not, else Q less than or equals to D and end module. So this is how the main conditional statements goes with this particular thing. If with respect to the reset value, if reset is 0, then the output is 1. If reset is 1, then the output goes to 0. That's how the conditional statements goes along with this. And this is a prominent step to remember. Why? Because we are writing this particular code in the behavioral modeling, and here the initializing of the inputs and as well as the output, and first line indicates a basic keyword representation and initializing of the basic keywords. Okay, so this is about a very low code based on the positive edge D flip-flop. And here, this is about the explanation. In the line 7 of the code uses the positive edge. So in line 7 use the positive edge keyword before the clock and reset inputs, sensitive list of the always block. As I said we are writing this code in a behavioral modeling. So obviously we have to represent the always at the rate. And the example that and the code that we are writing, it is under the edge triggering, right? So it is under the positive edge triggering of the D flip-flop. So that we are representing everything in the line 7. So pos edge, pos edge is nothing but the positive edge. What is this positive edge? Positive edge is nothing but it tells, representing the pos edge, it tells the synthesis tool of the always block. Okay, and it should be activated at the rising edge of the clock and reset. So we are considering the positive edge clock signal, right? So positive edge is nothing but it indicates the rising edge of the clock. If you are representing the negative edge, and it represents the falling edge of the clock. So here the signal will be activated at the rising edge of the clock and the reset signal. So why it is rising edge? Because we are considering it is a positive edge D flip-flop, and hence the rising edge of the reset will active the always block irrespective of the clock signal condition. So here as the code is about the positive edge positive edge flip-flop, positive edge, that means a rising edge flip-flop. So irrespective of the reset button or always with respect to the always block, we can represent the rising edge of the particular clock signal. And the reset of the D flip-flop is asynchronous. So we said that this reset button, certain reset buttons we have in the storage element. So this particular reset button in the D flip-flop, it acts asynchronously. Okay, it acts asynchronously. That means not with respect to time. There is no time. The reset button there's no relation between the reset and the clock signal, the time period. It goes asynchronously with respect to the designer's conditions. And when the always block gets activated, what happens? The reset button is checked. So here in the previous code, we have written always at the rate positive edge clock and positive edge reset. So here the reset always block will be activated the always at the rate. So always the keyword, it will be activated when the reset is checked. Okay, when the reset button is checked, then obviously the always button will be activated. See, when the reset button is checked, okay, Sometimes the reset may go 0 and sometimes 1 based on the condition. And this reset button is checked based on the always will be activated. And then if it's logic high, the D flip-flop reset to Q less than 1. So if the clock edge is going high, that means what? If reset is logic 1. So if reset is logic 1, what happens? The output goes high. If reset is logic 0, then output goes to 0. So if it is logic high, if the reset R is goes to 1, then the output of the flip-flop goes to Q less than or equals to 1. So it goes to high. And if reset is not a logic high, then the clock signal has the experience rising edge and the D flip-flop should get the value Q less than or equals to Z. So here we are observing two cases. One is when reset is equals to 1. When the reset is equals to 1, we are saying that the output may be less than or equals to 1. And if reset is equals to 0, if my reset is nothing but it's equals to 0, then the output goes to the with respect to the input. So output Q is nothing but the less than or equals to the input. So this is the two cases, case 1 and case 2. This is what we will observe in a general mechanism, in the general working of the D flip-flop with respect to the sequential machines. Okay. And then see, using non-blocking assignments and the blocking assignments. So now in the designing of our D flip-flop, sequential machines using the D flip-flop, we see blocking assignments and non-blocking assignments. So regarding the assignments, in the module 1 or in the module 2, we have already discussed what is an assignments, different types of assignments, and what are the statements and different types of statements. In the statements, we have discussed about the blocking and the non-blocking statements. So here, this particular coding, this coding that we have written with respect to the blocking assignments. So blocking assignments is nothing but a plain assignment operator with respect to LHS and RHS. This is a blocking. Non-blocking is less than or equals to. So the symbol which is used for non-blocking statement is less than or equals to, and the symbol equals to is for the blocking statement, and this is for the non-blocking statement. So this example, when we observe the blocking statement, we see module, block, and the thing that we are considering is a D flip-flop. For the D flip-flop, we have clock signal Q1 and Q2. And then input D clock. So D is the input and output Q1 and Q2. So here and then register Q1 and Q2. Always at the rate positive edge that we are considering begin. Okay, so here begin, initial, begin, else, if, end module and module. So module, end module, begin, end, if, and end module and initial. These are nothing but the keywords. So these are nothing but the keywords, and the under name for all the such keywords, comments, and all we are calling is a lexical tokens. These lexical tokens are already predefined in the Verilog library. So here in the blocking statements, we are representing with the module, whatever the statements, whatever the device that you are considering, for example, block. So this is nothing but the port list. In the port list, we are representing the output port first and then goes with the input ports and initializing the output and the input with respect to the variables, register, and then finally writing out with the keyword using always at the rate positive edge clock. And now begin. Begin says that Q1 is equals to D. So output is nothing but D, and one more output Q2 is equals to Q1. Okay, and then end module. So this is nothing but with the help of two D flip-flops, by considering two D flip-flop, how the outputs are obtained. This is what the coding says. So here D is an input, the same common input is given to another flip-flop. This is a D flip-flop 1 and this is D flip-flop 2, and the clock as well, the same clock is given to the D flip-flop 1 and 2. But when it comes to the output here, the output Q1 is equals to D. Okay, in one clock signal, and output Q1 is equals to Q2 in the another clock signal. So this is how the representation of the blocking statement. So blocking statement, this is nothing but the RHS, where you have the expressions, where here you have the vectors or else variables, and this is the LHS. These are the variables. LHS consists of the variables. Variables are nothing but the variables. It could be in terms of scalars and as well as in the vector form. So this is about the blocking state example under the D flip-flop. Coming to the non-blocking state. So here, improper use of blocking state and non-blocking state can lead to undesired functionality. So what happens if you are considering if you want to write the code in terms of blocking and unblocking, non-blocking statements, then you have to write each and every code with respect to all the constraints. If you are not following any constraint, then the output is observed to be undesired functionality. Okay, so the output will not be we will not observe any kind of output. So this example is about the non-blocking statement. So if you observe non-blocking statement, the operator that we use is less than or equals to. So less than or equals to is meant for the non-blocking statement, and equals to is meant for the blocking statement. So here in this non-blocking statement, the same module is a keyword, block, D, clock, Q1 and Q2, and the initialization and representations of the input and as well as the output, always at the rate positive edge. And then here the Q1, previously for the blocking statements we got Q1 is equals to D and Q2 is equals to Q1. This is for blocking statement. Whereas here for non-blocking statement, the left hand side is output Q1 which is equals to D, and the right hand side is the expression. So for this Q2 less than or equals to Q1, Q1 less than or equals to D, and Q2 less than or equals to Q1. So this is for non-blocking statement. And then if you observe here, same D flip-flop 1 and D flip-flop 2. So it's the same common clock is being given to the flip-flop 1 and flip-flop 2. The output, the input is D data and the output is Q. The same Q is given as output to the as input to the second flip-flop. So Q is the output of first flip-flop and it can be given as input to the second flip-flop. And then finally we are obtaining the Q2 as a second flip-flop output, Q1 as a first flip-flop output. So here when the two flip-flops, they are connected, they're connected one over the other, they're connected serially, right? So in this fashion we can say sequential manner that flip-flops are connected. So the output of one flip-flop is been given as input to the another flip-flop. But the representations of non-blocking statements, always remember for non-blocking statement less than or equals to, for blocking statement is equals to, less than or equals to, for blocking statement is equals to. So this is a small differentiation between the blocking and as well as the non-blocking statements. And here, if you observe the D flip-flop with respect to the synchronous reset in Verilog. So this is a coding for synchronous reset in the Verilog of the D flip-flop. So module D flip-flop, we are observing the synchronous reset. So the reset, as I said you, the reset can be asynchronously, we can use the reset button, right? But whereas if you are using, if there is a chance of usage of the reset with synchronously, then this is how we can observe module D flip-flop, synchronous data, clock, reset and Q. D and Q are the input and output, and as well as we have clock and reset. And the initialization of the inputs and output goes input, we have data, clock and reset, and output, Q is the output. Register is a keyword, register is a variable of the output, and always at the rate positive edge of the clock signal. Begin if reset is equals to 1. Okay, if reset, this is nothing but the case operator, in case operator. So case operator represents double equals to. So the if reset double equals to 1, then the output goes less than or equals to 1. Else, if Q less than or equals to data, that means what? If reset is 1, then Q will become, then Q is equals to 1. And if reset is 0, that means Q is equals to 1. If reset is equals to this 0, then Q is equals to D. And then N module. Okay, so synchronously, how the D flip-flop is going to reset with respect to the synchronous reset. And then we'll go. Many sequential machines, they implement the algorithms, isn't it? So many sequential machines, with the help of different algorithms, they can be implemented. That is multi-step sequential computations in hardware. So in the hardware, if you are modeling some device, if you're modeling some device, being a designer, you can use different types of algorithms, and those algorithms can be in one-step or multi-step sequential machines. So you can use one-step sequential machines and as well as the multi-step sequential machines. And the machines actively consist of synchronous sequential operations of the registers and data paths under the direction of controlling state machines. So here, as you are considering a sequential machines, so synchronously, if you observe the outputs, then you have some data path. The operations would be carried out with some data path based on the state machines and as well as the controlling the state machines. So each and every state machines will consist of the data which is present in it, and that data is obtained with respect to the clock signals. Okay, and then the state transition graph (STG). The state transition graphs indicates as transition the results from inputs that are applied when a state machine is in a particular state. So here the state diagram and state graphs, okay, state registers. So these are nothing but the graph. It represents the it presents the transitions, how the transition is taking place from one state to the another state, resulting the output which is based on the which is based on the inputs given to the particular present states. So here the state transition graphs indicates a transition that results from the inputs that are applied when a state is in a particular state. So when the particular state is transiting, when it transits the output, it represents that the particular output is being observed with respect to the inputs and outputs, and that can be represented with respect to the state transition graphs. And sequential machines are widely used that requires sequential activity. So in the yesterday's class, we have discussed when it comes to the asynchronous and synchronous sequential machines, most probably the designers will opt for the synchronous sequential machines. Okay, but the less consideration is given to the asynchronous sequential machines. So widespread is been given, or the high priority can be given to the synchronous sequential machines. And the set of state of equations synchronous sequential machines is always finite, because we have here in the sequential machines we have finite number of states, and so that we get the finite number of possibilities of the states, and as well as the possibility of the state, and the representation of the state machines will be infinite with respect to the inputs and as well as the output. And a machine whose state is encoded of n-bit word can up to 2 per n states. So here the encoding of bits can be observed. So if you are having n bits, the state is presenting the n bits, and then it can encode to n2 per n bits of information. So encoding part can also be carried out with respect to the state transitions. And the finite state machines refer to the clocked sequential machines that has one of two structures. So here in the sequential machines, as they are pertaining to the finite state and finite bits, so here it refers to the clocked sequential machines. Finite state machines refers to the clocked sequential machines, and they are kind of two types. So melee and mode. So here synchronous means with respect to the clock, and the clocked finite state machines are widespread used when it comes to the asynchronous and mostly in the digital systems. In the digital systems, synchronous sequential machines, that is with respect to the clocked signals, can be used widely. And synchronous sequential machines are characterized by the finite number of states which are driven by the clock in the state transition. So only finite transitions can be observed which are driven by the clock in the synchronous sequential machines. And fundamental types of finite state machines are melee and mode. These two are very basic fundamental state transition devices, or else mechanisms that we can see here in the melee and mode. The next state of the output in the melee machine, the next state of the output depends on the present state of the input, and the next state of the mode machines depends on the present state of the input, but also depends on the present state. But the output depends only on the present state. So here, this is a small difference between these two finite state machines. So Mealy and Moore. So in the Moore machines, in the Mealy machines, the output depends only on the present state of the input. Okay, the next only on the present state of the input, the output is depend. That is nothing but the Mealy. And in the Moore, the next state of the machine, the next state of the output depends on the present state of the input and as well as the present state of the particular state, present input and as well as the present state. So this is nothing but the Moore. So in that, in detail, we will explain, or else we'll come to know what is Mealy and Moore in the coming classes. I'll explain you there. So in both the machines, the next state outputs are formed by the combinational logic. So this combinational logic is nothing but the present state and the next state. So both the machines, the next state and the outputs are formed by the combinational logic. So this is about the Mealy and Moore, a small difference, and this is all about the synchronous sequential machines. So in the next classes, we'll be discussing more about the analysis of the synchronous sequential machines and the synthesis of synchronous sequential machines using the different tools in the HTL programming languages. So thank you for the day.
Like, share and subscribe. Hit the bell icon for more updates.